So we're going to start by talking about what constitutes an inference problem. And to do this, I've taken a bunch of examples across the sciences and engineering. I'm going to go through these one by one and talk about different contexts in which inference problems show up and can be useful in applications. So the first one we're going to talk about is this example at the top here from climate science. In climate science, we often have very detailed physical models comprising of differential equations that relate inputs to the system, such as solar flux from the sun or the human contribution to environmental variables which are relevant for climate change, like CO2 emissions. And through these differential equations, which are embodied in really detailed physical simulators, we're able to simulate different environmental variables, such as the temperature of the ocean, current flow in the ocean, flow of gas through the atmosphere or across the land. And through these detailed physical simulators, we can generate the value of particular variables which it would be possible to observe. So take temperature at a weather station, for example, or the sea ice level at the Arctic, or the CO2 concentration in the atmosphere in a particular location, like in Hawaii. So in climate science, we have these detailed physical models which relate these inputs to actual observed variables. And in practice, one of the problems is we don't know these inputs precisely. For instance, it's quite hard to measure solar flux accurately, and it's really hard to measure the human contribution to CO2 emissions across the whole planet. We can guess it, and we have some idea what it might be, but we can't exactly pin it down. Now, one example of an inference problem would be to work backwards from observed temperature measurements at a weather station, say, or sea ice measurements made from a satellite, and work backwards to figure out what the input and the contribution from humans to climate change would be based on those observations. So here I'd like to contrast these blue arrows, which are simulators or differential equations, and these purple or magenta arrows here, which are inferences that we might want to perform. And as I said, in this particular example, one key inference is to work backwards from observed temperatures and figure out, is climate change real? How much are humans contributing to it? How much is it just variability in the solar flux, for instance? There's another really important example of an inference problem in this context too, which is to take current temperature measurements or current sea ice level measurements and predict forward into the future and infer in the future what would those levels be. And so that's another example where we're taking known observed variables, the temperature measurements, sea ice measurements, etc., and then forecasting into the future what future unobserved settings of those variables would take in order to make decisions about their future. So that's one example from climate science. Let's go down to this sort of similar, at least conceptual example from astronomy at the bottom. So this is one taken from physics. There are lots of inference problems in physics. So in physics, once again, we have a detailed understanding of how the fundamental physical constants cause the physics of, let's say, the cosmos to evolve over time. And we can make observations of the cosmological variables that we can observe through telescopes, etc. So one of the most famous of these is the cosmic microwave background radiation, which is sort of shown here, for which researchers won the Nobel Prize for. And ideally, what we might like to do in physical applications is to take measurements of things like supernovae frequency and cosmic microwave background radiation throughout the observable universe and invert those measurements, combining them with the knowledge of physics that we have in order to estimate what the unknown physical constants are. So the physical constants, many of them are not given to us by theory. They're sort of unknown constants that have to be estimated from experiment. And so we'd like to go back from these experimental observations and estimate the physical constants. And of course, there'll be some uncertainty when we do that. So we'd ideally like to capture our uncertainty in those physical constants as well. And that's another example of an inference problem. So those two examples were from science. On the right-hand side, we have more engineering-y examples at the top. One absolutely pervasive example over the last few years is object recognition. So in object recognition, as I'm sure many of you will be familiar, you take unseen test images that you've not seen before. So here's a test image, and you pass it into your recognition system, and your recognition system's job is to carry out an inference, as shown by the purple arrow here. And the inference is what particular tags are appropriate for that picture. And the tags might correspond to things like the objects that appear in there, or some overall description of the scene, like it being outdoors, for instance. And so this is another example of an inference problem. We have some observed data, the test image here, and we have to infer from it the unknown tags that would be appropriate for that image. And in practice, what we mean by appropriate here is a human labeler might also have written down those tags if they were also presented with that unknown test images. So we'd like to infer what the human labeler would ideally label for this particular test image. So it's another example of an inference problem, and we'll look at problems a bit like this in the course, actually. Another famous example down below is speech recognition. Of course, this is very similar. We serve a automatic system with now a speech waveform shown here. This is a speech pressure waveform. It processes that waveform, and ideally what we'd like to come out of it is a sequence of text that would be the text corresponding to the words that were uttered to generate that speech waveform by the speaker in the first place. And again, that's moving from known stuff, the observed speech pressure waveform, to inference estimation of what the underlying sentence that the speaker was trying to say in the first place. And again, uncertainty here might be key. If you're using this to control a self-driving car, you might like to put uncertainty over the estimated sentence that you think the driver was trying to communicate to the car. So these are some examples, the last two from engineering. I could have listed hundreds of them. So things like being able to automate drug discovery. In drug discovery, you want to predict the properties that molecules will have before you synthesize them. And so you need a prediction system for predicting or inferring the properties of, say, a molecule from its molecular structure. Genomics, similarly, you'd like to analyze lots of genomic data and actually be involved in lots of different inference problems. So estimate the probability that someone might have a particular genetic disease, for instance, from their genetic material, or to cluster people who have similar genetic properties together. You might want to infer whether two people are similar to each other in certain respects. Collaborative filtering is another famous example where we need to estimate people's preferences or likes from their data. So we might want to, for instance, predict what films people like based on what films they've seen and what ratings they've given to those films. That's an example of another inference problem. And even error correcting codes, which are present on your computer, they try and figure out what the data should have been that was stored on your hard drive after it's been corrupted by bit flipping events. So error correcting codes try and infer what the true data would have been given the corrupted data that would be stored on your hard drive, and will inevitably be undergoing random bit flipping events because of imperfect hardware on your computer. So at the heart of our computer systems, error correcting codes are performing inference problems essentially in order to maintain the integrity of your system. So taking a step back and sort of distilling down what I've tried to communicate in this slide, the essence of an inference problem is essentially any problem where you have to estimate a set of unknown variables from a set of known variables. And often in those contexts, you know something about the relationship between the unknown variables and the known variables. So in the climate science example, it was a simulator, same for physics. In the object recognition example, it's probably a pile of data that tells you what actual labelers would have tagged real observed images with. Now, there's a little bit of terminology I'd like to talk about here, and the known variables are sometimes called observed variables. So I've probably already done this on the video. I've probably interchangeably used the word known and observed variables. They're the ones that are data that you've seen, you've measured in your weather station, or you've collected from people, labelers who have labeled images. Unknown variables are sometimes called unobserved variables. So they're like the physical constants or the human contribution to climate change. And there is a second sort of set of terminology that's used here that we'll also use in the course, and you'll see in the textbooks that are associated with the course. So unobserved variables are also sometimes called latent variables. They're latent because they are not observed directly. They're hidden. So you might also call this a hidden variable. So the goal of an inference problem is to estimate these unobserved variables, these latent variables or hidden variables, all used interchangeably, from these observed variables, given some prior knowledge of how the two sets of variables are related to one another. So that's the definition of an inference problem. And in the course, you'll see tons of examples of where such inference problems are useful, and will give you a set of tools for solving inference problems that will work in lots of different contexts.